Hello, AP Calc. It's just me, Mr. Wee. So I'm going to try to help you finish up with 2.2. Let's see if I don't know. My system's getting a little bit slower because I've been taping all day. But okay, so let's go ahead and continue where we were. Right, we were at squeeze theorem, if I remember correctly. Okay, come on. Okay, there we are. Okay, so I believe we left off here. So your notes might look a tad bit different from mine in terms of where things are organized, but it's the same thing. So we did squeeze theorem in 2-2 limits involving infinity, okay? And then we talked about how we had a limit approaching infinity as we have this sort of problem here, 1 minus cosine of x over x squared. And then we set up a range, and then what we knew about cosine of x, and then we made our range look a lot just like our current function that we're looking at, and then we squeezed it behind two other functions, essentially two new functions that we created, and then we found the limits of each of these functions, and then we squeezed the limit between these two functions, which happen to be, if we took the limit of that, we took the limit of those two functions, they ended up being 0. So in conclusion, if we were to squeeze the limit of 1 minus cosine of x over x squared, and it is to be between a limit of 0 and 0, then in conclusion, this limit must be equal to 0. Okay, so let me give you another problem for us to look at, and it's going to segue into our next point of our next topic in this section 2.2. Okay, so let's look at another example. Let me see if I can let's see if I can get a little focus going on here. Okay, so the example would be the limit as x approaches specifically negative infinity of sine of x over x. Okay, so in this case here, you knew that, just to clarify, you've learned that the sine, or the limit as x approaches 0 of sine of x over x is 1. Okay, as it approaches 0 towards the middle of an axis. Okay, but this, however, is different. This is going to the left, all the way to the left. This function is going to go all the way to the left. So this is going to be a little bit different. Okay, so first establish, okay, so you can pause this and try this on your own, but if you've unpaused it and you want to see the solution, here it is. Let's first establish a range that we're all aware of. If you graph the sine of x, it's oscillating, correct? Like this. It oscillates, right? Sorry, a little bit more evenly and symmetrical than this. But it goes up from, it peaks up at a y value of 1 and it goes down to -1. So the range would be 1. The sine of x would be between 1 and -1, right? So our goal is to make this look like this, our original function, okay? So we would divide this middle portion here by x, but we don't want to change the inherent value of the range, so that means we have to divide every guy by x as well, okay? So let's see here. So at this point, we're pretty much settled and finished here. We can take the limits of each of these guys going towards negative infinity. Negative infinity, so that'd be negative infinity of -1 over x. This would be the sine, or the limit of, as x approaches negative infinity. Sorry, that's written very poorly, but that's negative infinity. I don't know if you can see that, of sine of x over x, and sandwiched between the limit as x approaches negative infinity of 1 over x. Okay? All right, so at this point, let's go ahead and take a look at what this would look like. So I'm going to use either Graphing Calculator or Desmos.com, but for the purposes of better note taking, we're going to go to Desmos. So you can clearly see what to do, right, or how it looks. So I'm assuming that when you're graphing these things, or when you're graphing these graphs on a TI-83, you already know how to basically do that and zoom out. So for the purposes of better note-taking, I'm going to do it on something that's a little bit more clear, assuming that you already know how to use your TI-83, okay? So let's do -1 divided by x, okay? And then the other one will be +1 divided by x. And let's look. So what's in red here, and here is this graph for -1 over x. And then what's in blue is going to be here and here. That's going to be represents 1 over x. If we're approaching negative infinity, meaning it's going to go to the left here, okay? So you can kind of see the x-axis, just as a reminder, you're going to -2, -4, -6. We're going to go all the way to infinity. And then, in fact, let's just put in the actual function that we're looking at, which is sine of x divided by x. And let's take a look. As I zoom in, look at it. Just like what we expected, as long as your math is correct, you should be able to see that our main actual graph of sine of x over x is sandwiched between these two other functions that we created. Henceforth, the limits are also going to be sandwiched, or the limit of sine of x over x as it approaches negative infinity should be sandwiched between the limits of these two red and blue functions. And folks, if I look very clearly, what does it look like it's approaching? It looks like it's approaching a y value of 0 for all the graphs, but namely for the two outer graphs, if we really think about it. Or if you don't want to look at the graphs, you can just plug in negative infinity, 1 over negative infinity, and 1 over negative infinity. Either way, that looks like it's going to be 0, roughly 0. This, however, is really hard to see. Sine of infinity over infinity, I don't really know. So x goes to negative infinity of sine of x over x, sandwiched between 0 and 0. So in conclusion, because, I'm trying to scroll up using my mouse for a document camera. You can't really do that. Since it's sandwiched, the limit, this singular limit value of sine of x over x is sandwiched in between 0. In conclusion, we could say, therefore, the limit as x approaches negative infinity, I can never write this clearly, of sine of x over x will be 0. And folks, what do we call that when we approach a number, if we go to the left of a graph or a right to the graph, and it approaches one singular value? Does anybody remember what that's called? It starts with an A. I wonder what that is. Okay, we go to the left here, right? And it keeps riding along a singular y value, and in this case it's 0. We call that a horizontal asymptote. So that's going to be our next note right here. Okay, so let's move on to our next subject. So we did a sample problem that segues directly and beautifully into our next topic of horizontal asymptotes. And you will really see horizontal asymptotes when you take limits of infinity, or limits that go towards infinity for these functions. So like this, here's an example. So what we experienced before was a horizontal asymptote. This will be a horizontal asymptote too. If we ask for the limit as x approaches infinity, of 2 minus, so let me give you a difficult one so I could show you how you would work through something like this. 2 minus x over x plus 1 times x squared over 5 plus x squared. Okay, how the heck are you going to find the limit of that? That looks really, really complicated. Okay, let me show you a nice way to do this, right? So this is practice on how to solve for these types of problems. So eventually, if you're going to go towards positive infinity or even negative infinity, okay, so we're going to look at both. Actually, we're going to look at the limit as x approaches positive. This is positive infinity, and we're also going to look at the limit as this approaches negative infinity. I want to see if it's going to end up as a horizontal asymptote. The only way we're going to do it is if we solve this in a way that's algebraic. Because if I plug in infinity, you might not get a clear answer right now. Okay, so let's do it in a way where we can start to look at it, where we can kind of push in infinity and see what happens, okay? Because in this case, we have infinity divided by infinity, right? That looks kind of odd, okay? And we have infinity, like, I'm looking at just like the operation here. You can't have infinity over infinity typically. That wouldn't really work out. That's as, I think, to classic mathematicians, this and this, infinity over infinity, I'm saying like as if we were doing substitution, that's not really acceptable. That's considered to be undefined, okay? But we'll talk more about that in just a second. So let's take a look at this, okay? what we're going to do is first, let's put the 2 in similar denomination or denominator terms as what it's being subtracted by in this parentheses. So let's rewrite this. X minus infinity, or x going towards positive infinity. Let's multiply the 2 as if it's a function, or as if it's a number or a fraction of 2 over 1 times, and let's get 2 to have a similar denominator as this term, x over 1. So what we're going to do is we're going to multiply this by x plus 1 over x plus 1. Essentially, this, anything divided by itself, is 1. We're not changing the value of 2, we're just changing the way it looks. And then we're still going to subtract x over x plus 1, right? And then this is still going to remain the same. So I like to take steps. I like to go step by step here, okay? And, I'm not going to write the limit as x approaches infinity. I'm just going to write lim, okay? Just to make this a little bit quicker. So this is 2 times x plus 1 over x plus 1. Again, don't cancel it out. I know you have that urge to just cancel it out, but that was the whole point, was just to make it look a little bit different from what it originally was. So that way we could actually start kind of making these guys mingle, right? So this will be subtracted with x for x plus 1, and then this over here still be unchanged, x squared, 5 plus x squared. And then let's do that again. That'll be the limit of, so let's multiply this out. This is 2x, 2 times x and 1. So this is 2 times x, that's 2x. 2 times 1 is 2. And then we're going to subtract the x. And they all have the same denominator, so we could all put it over the same fraction now. It's going to be x squared over 5 plus x squared. Okay? Now that we have this and we have fractions being multiplied to each other, we don't have to worry about them being the same denominator. What we can do now, if you remember multiplying fractions, is you just multiply the numerators and the denominators together. So the limit would be, oh buddy, this isn't going to look pretty, 2x plus 2 minus x times x squared over x plus 1 times 5 plus x squared. You can take a minute to solve this on your own. I'm going to do it really quick without too much explanation, because hopefully you understand the algebra. I'm going to distribute the x squared of these three guys, so that should be 2x cubed plus 2x squared minus x cubed, okay? And the bottom, this should be, let's see if I do a FOIL or whatever technique I choose to do this, 5x. That should be x cubed. Okay, and then this should be 5, and then this should be x plus x squared. Okay, and now I'm going to rearrange this, okay? Let's see, did I do something wrong here? I feel like I did something wrong here. No, it looks about good. Let's see. Sorry, I'm looking back at my other notes at the moment, like right now. Yeah, looks like everything's to be good. Okay, so I'm going to arrange this in a way where my highest degree x value is going to come first. So it's going to be negative x cubed plus, or actually, oh, I see. These two will combine. 2x cubed and x cubed will combine because they're like terms. So that should be positive x cubed. And then 2x squared will be there, okay, on the top. So that's all I have for the top. And then on the bottom, let's see if I can combine any like terms. I don't see any. So I'm going to do x cubed first. Then x squared is my next highest degree exponent variable. And then plus 5x plus 5. There we are, okay? And then let's remind ourselves that we're looking at as it approaches infinity, okay? Now the next step, you got to kind of trust me on, because we're approaching all the way to infinity. We got to look at the two exponents that have the highest degree value, okay? So we have one clear fraction now. There's no addition on the outside of any other terms. Everything is all under one fraction. So here's what we can do now in conclusion, okay? If we're going to infinity, these lower degrees are going to be negligible, right? Their values are going to be negligible. You're going to look at the highest values that you have left. And that's all that's going to really matter, because if you have infinity, whatever the high, like super high values cubed and super high values cubed, it's going to outweigh what these guys present to the overall value at the highest numerical values that you can even comprehend. Okay? So we look at these guys and let's see how they interact. X to infinity, if we only focus on x to the third power over x to the third power, and only focus on those two highest degree values, guess what? We're looking at x over 3 divided by x over 3. That essentially will cancel out and to become 1. And the limit as x approaches infinity of any constant is just 1. You can rewind that a few times to figure out what just happened here, okay? But it does make sense. If I do that with x approaches negative infinity to the opposite side now, okay, you can graph this and check this out. Again, you're going to be left with the same situation of x over 3 divided by x over 3. This is going to be equal to essentially the limit as x approaches negative infinity of 1. And then guess what? That is still going to be 1. Okay? So that's your horizontal asymptote. Did a horizontal asymptote occur with this specific function by the end? Yes. Okay? All right. That is good. Let's move on now to another problem. Okay? So my plan is to go through one more problem, then give you a sample problem to try, and then you can pause and I'll just show you the answer. And then I'm going to make one more video on vertical asymptotes. Okay? So here's one more. Here's f of x is equal to the cosine of 1 over x divided by 1 plus 1 over x. And then we're going to have to take the limit of this. So let's take the limit. So we're looking at what is the limit as x approaches positive infinity of f of x, which is, again, this equation up here, and the limit as x approaches positive or negative infinity of f of x. Okay? So let's take a look. If we take the limit as x approaches infinity for this, can we substitute it? That should always be a question. Can we substitute the value? Let's see. I like anything that is just a number over x, because when you have a whole number being divided by a variable, you can conceptually put in a very high number. Anything that's divided by a super high number is going to approach 0. Sort of like 1 over 2 versus 1 over 100. Which one is going to be the smaller value? That's like 50%. This is like what? Like 1%. If you, or this is 0.01, this is 0.5. This is a way smaller value. So you can see the higher you go in the value in the denominator, you will approach 0 eventually. If you did like 1 over a trillion or a billion or any of these numbers that you could think of, it gets closer and closer to 0, right? 0.01 versus 0.5, right? This is getting closer to 0. So this over here, if you plug in infinity, positive infinity into here, okay, you will end up getting the cosine of 0 over, let's check this out, 1 plus 1 over infinity. So it'd be 1 plus 1 over a huge number, which would be 0. And you would get the cosine of 0, if you remember your math, is 1. You can check that on your calculator. What is the cosine of 0? Or you can graph it and you can see it's just 1 divided by 1. That's it, folks. That's all you had to do. That's it. Okay? Will it be different with negative infinity if I go all the way to the negative numbers? Well, let's check it out. The cosine of, let's plug in negative infinity. It'd be 1 over negative infinity. If you think about it, even if you put a super high number to the negative side, it's still a super high number. It's still going to go to 0. Okay? I know it's kind of weird, but think about that for a second. The same applies to the bottom. 1 plus 1 over x, it'd be 1 over negative infinity, which is going to be eventually come towards, or you're going to approach a super small number. You're going to have the same effect of 1 divided by 1, which will give me 1. That's it. That's not that bad. Think about it for a second. If you have any questions, come and see me for tutoring. But hold on, I got one more for you that you can try. Okay? It'll be the f of x of cosine of x. If you don't want to try it, you can go ahead and just see how this plays out. I'm not going to go through the steps here. I think I'm just spending too much time with you. Again, find the limit as x approaches positive infinity of f of x, and the limit as x approaches negative infinity of f of x. You can pause it and try it, but this is what you would end up getting. Okay, it's this problem right here. Okay, so you could pause it and take a look at so this is the question, here's the function, and then here's the math that you would end up doing, and you should get about -2 as your final answer. Okay, all right, guys, my next video is going to be on vertical asymptotes, so I will see you then. Otherwise, you guys take care and have a great day. The vertical asymptotes video should be a lot shorter. Okay. All right, guys. Thank you for listening. Goodbye.